Welcome back. This video is going to give you a high-level summary of some critical concepts from the theory of estimation that we're going to need. I'm just going to mention that there's a link to a video that gives you, more detailed discussion of these concepts that you're welcome to watch if you're curious. But this is kind of the most important concepts that you need to know for the rest of this class on the theory of estimation. So the question is, how do I evaluate how good an estimator is? And so let me just go over to my paper here, and I think it's almost easier to talk about these concepts on paper. So the way that this is usually discussed is that we have some estimator, and that's traditionally called theta hat. Let theta hat estimate parameter theta. All right, so I've got a sample of data, and from that sample of data, I compute this theta hat. Now, to make this a little bit more concrete, if we go back to the slide that we're actually talking about, the prime example of this could be, B is an estimate of beta in regression. Or, there's countless other examples of this. For example, x bar can be an estimate of mu, or s squared could be an estimate of sigma squared. Would all be, concrete examples of this. But we don't want to use a very specific symbol for this. We use theta hat and theta as the more general symbols. All right, so the next concept we need is that of bias. So the bias of some statistic is going to be the expected value of that statistic minus the mean, so minus the parameter. Okay, so that is the bias of a statistic. So I'm just going to take us over and draw a picture of the sampling distribution of some statistic. Now, let's just say that this is the true value of theta. And so if this helps to make it a little bit more concrete, theta could be a mean. And so if I could do a census on the entire population, I would know the mean, and that would be this value. Now, if I had a distribution that looked like this, okay, so this is a sampling distribution of this statistic. So this would be like the distribution of x bar. Across different samples, I would get different sample mean values, and those follow a normal distribution. Now, the point I want to make with this is this distribution is centered around theta. Okay, so here, note that the expected value of this statistic is exactly equal to theta, and therefore we would say that theta hat is unbiased. So unbiased estimate of theta. So the way I always like to describe this is, on average, we're right. Okay, so sometimes when I draw a sample, my estimator, whether it's x bar or the slope or s squared, is too high. Sometimes it's too low, but on the average, I'm getting exactly the right value. So that is an unbiased estimator because the bias is 0. Let's just consider another estimator. So I could have another estimator that looks like this. And notice that the expected value of the red estimator does not hit theta. Okay, so this would be a biased estimate because on the average we are below what we should. So I used to teach from a textbook that gave an example of a biased estimator, which is the dishonest butcher. So you go into a butcher shop and you say, I want that piece of meat, and the butcher puts it on a scale, and let's say the butcher is dishonest and he puts his thumb on the scale so it weighs more than it should. Okay, so what's going to happen is, I end up paying more for this meat than I should because the butcher's thumb is on the scale. So that would be an example of where my estimate is biased. Now, in this case, I drew it below the statistic. In the case of my dishonest butcher, the packages would always weigh more than they should. All right, so that's one key property of estimators. Another key property is how stable is the estimator. So we often call that the variance of the statistic. So the variance of that statistic is equal to the expected value of, well, theta hat minus the mean of theta hat. All right, so this, we'll just have, so this would be, what is the typical amount that this statistic is off from its mean? Likewise, the variance of this statistic would be how far is this off from its mean. So we can sometimes call this the mean of theta hat. So this would be the mean of this biased theta hat. All right, so we like our estimates to have small variance, because then what that means is we're close, to the parameter. If we have a low variance estimate. Actually, let me correct what I just said. We're close to its mean. So let me just kind of remind you of a very famous result. So in the case of x bar, we know that the variance of an x bar, a very famous formula, is sigma squared over n. So if I were to estimate a mean, and as I increase n, the variance of the sampling distribution is going to improve. So I'll just go draw that for a second. Here's the sampling distribution of x bar. And x bar we know is actually unbiased, so the mean is mu. And let's say I had a sample of size, say 25. So with a sample of size 25, this would be the sampling distribution. So this would be the distribution of x bar, where we have sigma squared over 25. So the standard deviation would be sigma over 5. Now if I increase the sample size to 100, the sampling distribution would look something like this. All right, so the variance of the red distribution would be sigma squared over 100. And so notice we're much closer on the average to the statistic than with this than with a smaller sample size. So this ought to make a lot of intuitive sense that when you draw a larger sample size, you're going to be closer to the statistic than when you have a smaller sample size. And so that's some fundamental intuition from basic stats, but I think it clearly illustrates this concept of the variance. So the last kind of property of an estimator that I want to discuss is something called the mean squared error. Mean squared error, or the MSE. So the definition of MSE is it is going to be the expected value of theta hat minus theta squared. So the way to think about this is, how far is my statistic from the parameter? Not how far is the statistic from the mean, which is what I have with the variance, but how far is the statistic from the thing I'm trying to estimate. So there's a very famous theorem, so let's just call this theorem, this equals the variance of my statistic plus the bias squared. So the bias of theta hat, and we could stick brackets around this, squared. So this is called the bias variance trade-off. And this is a very important result, and we're going to be dealing with it for much of the rest of the quarter. So let me just go draw a few pictures for us to understand what this is about. So we could talk about regression. So that's what this chapter is about. But rather than having a p or p+1 dimensional slope vector, let's just say we had a very simple model where y sub I is equal to some beta times x sub I plus some errors. So I don't have an intercept, all I have is a slope, and I estimate this with some estimator b. Okay, so b is an estimate of beta. And I'm not going to claim that this is the OLS estimate for right now, but it's just some estimator. And so we could consider a couple different sampling distributions of B. So here's my B. So B is like, think of this as like a theta hat. This is an estimate. And this is the true parameter beta. So what we would love to have, this is the ideal world, would be a sampling distribution of my B that looks like this. And so I'd like to point out a few things about this. In this case, the expected value of B is equal to beta. So the center of this distribution is over beta. So I would say that this is unbiased, or it's at least extremely low bias. But also, I have a low variance. So the variance of this beta hat is very small. And so this is like the best of both worlds. So the mean squared error, of my statistic is just going to be the variance of that statistic plus the bias of B squared is going to be small. So this is a small variance, and okay, the bias in this case is 0 squared, and so this is like the ideal situation where my my estimator has a very low variance. But sometimes we might have a situation where the variance of my estimator is not so good. So this would be an example of, so I'm just going to draw in red here. This would be high variance. So it's high variance compared to this nice blue estimator. But the nice thing about this is it's low, it's unbiased. So this is centered exactly at beta. So in this case, we'd have kind of a high mean squared error because the variance is quite large. Well, I'm now going to go grab my pencil, and so I hope you can distinguish between the blue pen and the pencil. Sometimes we'll have the opportunity to have an estimator like this. So what I'm trying to do with this estimator is make this biased. So in this case, this would be the mean of my estimate. And notice that for this estimator, it's biased. So the expected value of B, maybe I should call this B3. We could call, this is B2 and this is B1. So the blue is B1, the red is B2. The variance of this is actually less than beta, so it's biased. But B3 has a small variance. So at this point, we probably prefer the B3 estimator, the pencil one, over the B2, the red one, because on the average, we're closer to the parameter with this pencil distribution than with the red distribution. So what I've tried to show here is the mean squared error of my pencil estimator is actually less than the mean squared error of my my red unbiased but unstable estimator. All right, so you're probably wondering, how does this ever come up? Well, it comes up in what we're going to be talking about this week, which is shrinkage estimation. So the whole idea of shrinkage estimation is that we're going to have a biased estimate of the slope that hopefully has lower variance than the OLS estimate and much lower variance, to the point where the mean squared error is actually better. All right, and so that's what this whole unit on shrinkage estimation is about. So introduce a bias that reduces the variance that gives us something with a lower overall mean squared error. So we will see many examples of this coming up, and I hope you have some intuition now of what I mean by the bias variance trade-off. So I'm going to introduce a small amount of bias that makes the estimate much more stable, and the net result is that I expect to be closer to the parameter than I am with an unbiased estimator. I'll just mention that there's a famous theorem called the Gauss-Markov theorem. Gauss-Markov says that the ordinary least squares estimates that we've used, throughout the class are said to be blue. So what does blue mean? So blue is an acronym that means the best, meaning lowest variance, unbiased, so the best linear unbiased estimator. So we cannot do better than OLS in terms of producing a low variance estimate, but this doesn't mean that it has the lowest mean squared error. In fact, a very famous theorem called the ridge existence theorem says that there exists a ridge estimator that beats OLS on mean squared error. So it's biased, but it has lower mean squared error. And so we're going to be exploring these biased estimators this chapter.